Hi everyone. In this video, we're going to look at a slightly more complicated example of calculating work. So for this example, let's suppose we have a conic container with radius and height as shown. And let's say this cone is filled with liquid to a depth of 3/4 of its height. The density of this liquid is denoted by the Greek letter rho, just like the previous video. And the question is, how much work is required to lift all the liquid out of this container? In the previous video, we saw that this type of problem can be approached by slicing our liquid into a bunch of thin disks. If we add up the work done on each individual disk, we'll end up with the total amount of work. To help us with that, we form a set of x and y axes as shown, and that just allows us to designate the position of our disk as a y value. And the thickness of our disk then would be dy, a small change in y. We know that the work done on this single disk would be force multiplied by distance, so let's start with the force. The force required to lift something would be equivalent to its weight, and from high school science, we know that would be mg, where m is the mass and g is 9.81. But we don't yet know the mass of this disk, so let's see if we can figure it out. We know that mass is equal to density multiplied by volume, and the density is rho, but what's the volume? Well, since this is a disk, we know that would be pi r squared dy. Just be careful that this r represents the radius of the disk, which is not the same as the radius of the cone. So it's very important that you don't call this capital R. I've chosen to call it lowercase r instead. And with that, we're done calculating force, so let's look at the distance. Remember that each disk only needs to travel to the very top of the container, so the distance traveled is represented by this vertical distance in our diagram. And as always, a vertical distance can be viewed as a difference of y-coordinates. Due to the position of my axes, the y-coordinate at the top would be h, the same as the height of the cone, and the y-coordinate at the bottom would be y, the same y value that was used for positioning our disk. So taking the difference of these, we find that h minus y is our distance traveled. And now all of this multiplies together as force times distance to get the work done on this disk. All that remains now is to add up the work done on all the disks, and that's done by taking the integral of dw. The constants being multiplied here are rho, pi, and g, so they can be pulled out front of our integral. It's important to recognize that lowercase r is actually not a constant because the radius of the disk changes depending on which disk you look at. So in other words, this radius lowercase r depends on the y value. So it's not a constant, we can't pull it out. So here we've got our integral, but what are the limits? Just look to the diagram and identify the position of the first and last slices, and I'll leave it to you to check that those are y equals 0 and y equals 3/4 h respectively. All that's left now is to calculate this, but there's still one obstacle preventing us from doing that, and that's the fact that lowercase r isn't a constant. If we want to calculate a dy integral, then y needs to be our only variable. So we need to find a way to express lowercase r in terms of y, which theoretically should be possible since we know the radius of the disk does depend on the y value, so there should be some relationship there that we can find. The key to doing that is to look at our diagram and remove all the distracting information. By doing that, we can see the formation of similar triangles. Let's see if we can identify the dimensions of these triangles. On one hand, we have the big triangle with sides of length capital R and capital H. And there's also this little triangle with sides of lowercase r and what? What is this length of this vertical side? Well, we know that the variable y was used for designating the position of our sample disk. So by subtracting the y-coordinates, this vertical distance can be calculated as y minus 0, or in other words, just y. Now from high school, you should know an important fact about similar triangles is that if we divide the length of any two corresponding sides, we always end up with the same value. So for example, if we divide these two corresponding sides, we get little r divided by big R. If we divide these other two corresponding sides, we get y divided by h. And for similar triangles, we know that these ratios must be equal. This establishes a relationship between r and y, and with a bit of basic algebra, we can solve that to get r in terms of y, which is what we wanted. So next, we're going to plug in this expression for lowercase r into our work formula, which gives us this result. And now that y is the only variable, we're ready to calculate this integral. So pause here and give it a try for yourself, and if you're ready to see the solution, let's continue. My first suggestion would be to pull out the constant factor of r squared over h squared. This isn't strictly necessary, but it's nice to just get these out of the way. Next, we notice that our integral contains multiplication, which is problematic for finding antiderivatives. So to avoid that, we should expand this out by multiplying y squared into the brackets. Now we've reached a point where we're just taking the integral of a polynomial, so the rest of the details, although a little tedious, are pretty straightforward, and you can check these for yourself. The only tricky part here is recognizing that h is a constant, so you have to treat it as such when finding your antiderivative. But that's all I have to say about calculating work, so I'll end the video here and see you next time.